Alright, so no warm-up today. We'll go ahead and get started. The first thing I'll do is I want you to take out your quizzes that are due this morning. And I'm just going to walk around real quick, take a look at them. You will be turning those in later today, but right now at the start of class, I just want to walk through and if you open it up for me so I can see that you made it most of the way through or all the way through. Alright, so the idea is we're going to do a course review today. We're going to start at the beginning of the course. We're going to talk through all the big ideas, have you do some kind of practice problems along the way. Along the way, we're going to talk about some of the questions from this quiz. At the end of class, I'm going to collect them and pass out the solution key to them. Okay, so you are allowed to look at them, maybe tweak an answer or two. That's fine as we go through this, alright? I'm just make sure everyone has done the work through completing it here. Okay, so the course review. Alright, sometimes it's just good to kind of go back and see this as an overview, kind of see the big picture. So often you're kind of going through the course and you're seeing all the small details lined up next to each other. You don't ever take a chance to step back and see the big picture here. That's what we're going to do here. So the beginning of the course, chapter 1, we saw it was all really about different ways to represent systems. Alright, so we looked at the same thing over and over and over again with different notation essentially. And so to kind of recap all that, we said that we could represent these linear systems as linear systems, sets of equations, or we had this augmented matrix here, or a matrix equation, right? Matrix times vector equals vector, or a vector equation, which is just the weighted sum of the vectors equal to some other vector. And then later we talked about also representing as a transformation, where we essentially have some vector x and we are mapping it to the result. Result of a times x, or the b vector. But all those ways to represent the same thing. So that was one of the biggest points actually from chapter 1, just that all these things are the same. If we wanted to solve a vector equation, we just wrote the augmented matrix. If we want to solve the matrix equation, we just wrote the augmented matrix. And so we wanted to solve those things. So the next big topic was solutions. What are solutions? What do they look like? And we saw that solutions were just values, x1, x2, x3, whatever the dimension was, that gave us true statements. So if we scroll back up here, it was an x1, x2 we could plug in here to make that true. Or an x1, x2 that we could plug into the matrix equation and do the multiplication and get a true statement. So it's just values that worked. So we could always test our solutions once we found them. And how did we find them? Well, we had a couple options here. At the very beginning, all we had was our row-reduced echelon form. We would take some matrix, put it into row-reduced echelon form, and find out if we could find solutions or not. We found out that sometimes there were no solutions, sometimes there was one solution, and sometimes there was infinitely many solutions. And later on, we had an alternative way to solve these. We could actually find the inverse of a matrix. So instead of just always taking our forms and going here to find the solution, we found out later that we could actually just stick with the matrix equation form, find the inverse matrix, and use that to solve for x. So, all that's kind of a quick recap of the first part of chapter 1. Let's try one. Solve this equation. Take a second and go through this solution here. And reviews are a little tedious just by their nature. They're very tedious if you just hear me talk the whole thing. So we'll kind of review a little bit and grab a couple problems from each topic. All right, keep these ones on a separate piece of paper too. I'll collect these ones at the end as well. Do it quick, do it done. By all means, check with the calculator. I encourage you to do that. But no one should ever leave the exam earlier. Go back and check all your solutions with the calculator. So that's a slow process if you haven't practiced using your calculator before. All right, there's my solution. So essentially we threw this into an augmented matrix, sort of. I didn't really augment with that B value. Why is that? Zeros don't matter. I could augment with B, but the row operations won't change that, so I'm just going to save my time writing that extra column of zeros, but I know it's still there. So any questions about the row reduction to this reduced row echelon form? Or this reduced row echelon form should be unique. This should be the only option for your reduced row echelon form. All right, then maybe the trickier part, actually writing this thing into parametric solution form. So I write out my equations. There really was no equation for x2, but x2 equals x2. It's the free variable. I can see it's a free variable from this form. There is no pivot position in that second column. So after that, I write out what each of my values are. Remember, the solution is just a x1, x2, x3 that actually work. So x1 is equal to negative 2x, or negative 2x2. And x2 is just equal to itself as the free variable. x3 was equal to 0. That's what the second equation told me. x3 is equal to 0. And I just factor out my parameter, and I get negative 2, 1, 0. So 1, crooked 1, crooked 1. Any question about that one? All right, and the big follow-up from this is that just like we could represent our systems, we could ask for that same process a whole bunch of different ways. So find an x1, x2, and x3 such that this is true. I'm asking the same question. Solve the homogeneous system here. I would say solve the homogeneous system. That would be another way. I could ask, are these vectors linearly independent? And if I wanted to find out, I would throw it into my matrix and I would row reduce it. And what would I find out in this case? Are they linearly independent? No, they're not linearly independent. Because when I look at that row reduced echelon form, for them to be linearly independent, I would have to have a pivot position in each column. Right, the pivot columns are the linearly independent columns of the original matrix. So when I look at this, I can find out which two of these three vectors are linearly independent. Which two do I want to grab?
First and third column.
First and third. These mark those pivot columns. I don't grab this column and this column, or this column and this column. I go back to the original matrix and grab the first column and the third column. Okay, so I can ask all those questions and kind of tell me to do the same thing. Right, write out the row or the augmented matrix, go through the row reduction. So they're not linearly dependent, so that should answer the next question. Do they form a basis for R3? They do not form a basis for R3, because a basis requires me to have, for R3, I need 3 linearly independent vectors. All right, so that was chapter 1, all these different representations for the same thing, and therefore that solution could answer a whole lot of different questions. And of course, there was a lot of terminology on the way. What does linearly independent mean? What does a basis mean? What does it mean to span? All those key verbiage that we learned in chapter 1. This goes back to some of our questions from the quiz already. So for instance, 7b, a linearly independent set that spans a space. What was that one? A basis, right? That's what it took to be a basis. Here, we don't have a linearly independent set. And if we broke it down to just the linearly independent vectors, then they wouldn't actually span the whole space R3. We just have 2 of them. Okay? All right, so finding out whether a set of vectors is the basis is one question that might lead to the solution process. So for number 1a, a set of 2 vectors could be a basis for R3. True or false? False, right? We need at least 3 vectors. Because if we go through that process and we write them all out, if I just had 2, 1, 2, 3, 4, 5, 6, what would be the problem? Could they be linearly independent? Certainly could be, but they couldn't be onto. Right? So to be independent, I need a pivot position in every column. To be onto, I need a pivot position in every row. Okay, so this same process was for 2a, so we just repeat this process for that one. Any questions so far? All right, so then we kept going. Chapter 2 really focuses back on the matrix equation. We learned a whole bunch of operations, so here's a couple operations. See if you can answer these 3 real quick. So first do the multiplication of those 2 matrices. And I'm giving you a matrix, find its transpose and find its inverse.
So we have 2, 1, 2, 2, and 2, 3. Let's practice working with matrices.
as always with these reviews, we're going to go through a bunch of stuff. We're going to go through it pretty quick. But a big part of the review process is to identify your weaknesses for you to practice on. So as you're going through these, if you start doing some of these operations, like, boy, that took me a while. Right, that's a red flag. So mark that down as when I go to review, this is the topic I'm going to hit hard. All right, there's my solutions. Once again, you want to be able to do this multiplication fast enough where it feels natural. You want to be able to go through this relatively quickly, because it's going to be smaller parts of bigger problems later on in your studies. So a whole bunch of different ways we can view that multiplication. Now, the way I do it is I take this matrix and I kind of pick it up and turn it on its side. That's definitely one way to visualize it, but it's not the only way. So if that way helps you, more power to you. If it doesn't, go back to the definitions. Here I would take this matrix essentially times the first column. So I take this value, 1 times 1, plus 0 times 0, plus 1 times 1, that gives me my first term. And then I go down and do the second row times the first column. So that would be 1 times 0, plus 0 times 1, plus 1 times 2. That'll give me the next value. So essentially it's this matrix, call it B, times this first column, call it C1. That's going to give us the first column here. And then that matrix times the second column will get the second column. So that's another way to visualize it. Transpose is flipping the rows and columns. Notice the diagonal elements stay the same. And the inverse, we have that nice little definition for a inverse of a 2 by 2. So it's 1 over the determinant. The determinant is just this product minus this product, so I have 5 minus 6. And all I do is flip the strong diagonal and change the signs of the weak diagonal. Finish up the calculation here. So any question about those two? Those three? All right, of course, that's the inverse of a 2 by 2. We talked about it in general for larger matrices. We have a more formal process here. We essentially augment our matrix A with the identity of the same size. And we just go ahead and do the full row reduction. We can only have an inverse matrix if our matrix row reduces to identity. Right? So if we're doing the row reduction and we can't get to here, there is no inverse. If we can get to here, then this becomes the inverse. Those row reduction operations on identity kind of turn it into the inverse matrix. Okay, so that really got us through 2.1, 2.2, and 2.3, really about working with matrices. After that, as we got into 2.8 and 2.9, it was the introduction to subspaces. Once again, 2.8 and 2.9 were really a condensed version of all of chapter 4. We start talking about subspaces as taking a large space and looking at just a small group of vectors within that space, a subset of that space. So the question is, if we just take a small group of vectors, does that form its own vector space? And that idea, sometimes it does, sometimes it doesn't. For that subset of stuff to form a subspace, that satisfies our three properties. It contains the zero vector, closed under addition, closed under scalar multiplication. And those ideas just meant that if we take any two elements of our subset, if we add them together, we're still in that subset. We can't add our way out, we can't scale multiply our way out. So that relates to problem 1b from our quiz. 1b said if H is a subspace and U and V are in H, then U plus V must be in H. Is that true or false? True, because that's essentially which of these properties? Closed under addition. So that's really the definition of being closed under vector addition. And so because we said H is a subspace, it has to satisfy that. Those are our three big properties of subspaces. Then we talked about two specific subspaces, the null space and the column space. These are both subspaces of larger spaces. So we have their definitions here. The null space is the set of all solutions to the homogeneous equation. So these are both spaces that are related to the matrix A. And the column space is the span of the columns of A. Now the column space specifically, we can kind of recharacterize a couple different ways. It is all possible outputs. Right? It's all the b's from the equation ax equals b. It's the range of A. And so we have these two definitions for these spaces. And before we talk too much about them, we have to kind of understand they're subspaces. That means they're subspaces of some larger space. Well, what space? Well, if A is a M by N matrix, so here's my matrix as M by N. So if those are marking rows and columns, what are the dimensions of this matrix? So I'll write some numbers in here. 1, 2, 3, 4, 5, 6. What are the dimensions here? It's a 2 by 3. 2 rows, 3 columns. When we talk about this as a transformation, so I could say A takes vectors that live somewhere and maps them to vectors that live somewhere. And so it's going to take this X vector over here. And it's going to map it to some B vector. So the question is, how big is X and how big is B? How big is X? Could this be X? Why not?
Because it doesn't match with the inside value.
Absolutely. I couldn't do the multiplication. It has to be x1, x2, x3. It has to be a vector in R3 for me just to be able to multiply them. All right, so that means A is taking vectors from here. So X lives in R3. R3 is a vector space. It's a set of all lists of 3 numbers. That's what R3 is. And when I do that multiplication, what's the size of B? Will I have B1, B2, B3? I won't, right? When I add those up, I'm basically taking a linear combination of these columns. X1 times this column, plus X2 times this column, plus X3 times this column. If I add up a bunch of 2-dimensional vectors, I'm going to get a 2-dimensional vector. So it has to be only B1, B2. So B1 and B2, my output, that vector B, is a list of 2 elements. That means it lives in R2. So in this case, A is a mapping from R3, R2. The null space are the solutions. It's not all the X's. It's not any x that we can take and multiply a. It's only the ones that when I multiply, I get to 0. So it's not all the vectors in R3, but it must be a subset of R3. Right, so in this case, the null space of A must be a subset. There's my notation for subset. It was a little confusing on the quiz. Right, subset, or subspace. The subspace of R3. Or in general, if this is an M by N, it's a subspace of R what? M or N? N or M? N. That's right, we kind of write out our example. The example tends to make sense. The M's and N's don't make sense, right? It's confusing. It's easy to get backwards. So what I encourage you to do if you get confused is write out like a 2 by 3. And then just see which one is M and which one is N, and that should help explain it. In this case, the null space is a subset of Rn, and the column space would be a subset of what? Rm. All right, any questions about those two? So that would relate to C and D from number 1, your true and false. Of course, we had to find these things. So if I said if A was equal to 1, 2, 2, 4, describe the column space and the null space. So that's the problem to work on paper. Here's your matrix A. Describe the column space and the null space of A. Or it isn't a quiz, so if you have questions, raise your hand or whisper to your neighbor or check your notes. Whatever it takes to get started. So we'll be plugged in this page at the end. We'll go through all the solutions, but all right, both of these questions, pretty much all the questions related to null space and column space, are all answered just by doing the row reduction. So once again, we don't have a whole lot of tools to deal with this stuff. We're going to row reduce pretty much everything. It's really the interpretation that's going to help us here. So I'm going to take this matrix and I'm going to row reduce it. So in row reduced echelon form. 1, 2, 0, 0. Right, just one row operation gets me right to row reduced echelon form. And so this is going to tell me both about the null space and the column space. It tells me about the null space because the null space is just the solution of that homogeneous equation. I should put a 0 vector up here, of course. So really there's an invisible augmented column of zeros at the end of that. But once I do the row reduction, I start to look at the equations again. So this says x1 plus 2x2 equals 0. And my equation for x2 would be what? x2 equals x2, right? Because it's just my free variable. So my solutions to the homogeneous equation would look like negative 2x2 and x2. Or they would look like any number times negative 2 and 1. So any number times negative 2 and 1 would be a solution to the homogeneous equation. Negative 2, 1, negative 4, 2, negative 6, 3. Any number times that vector negative 2, 1. Negative 2, 1 is really a basis for the solution space. Right? But the solution space to the homogeneous equation is just the null space. So the null space of A is the span of its basis vectors. It's the span of the one vector in this case, negative 2, 1. That's one way I could describe the null space. Oh, it's the span of this thing. Or I could say, well, how would I describe the null space? I would give you its basis vectors. I would say a basis for the null space is negative 2, 1. That's the best way to describe a space, is to give us the basis. Because the basis allows us to build every vector in the space. So that's how the row reduced form gives us the null space. Well, what about the column space? Well, the column space of A, by definition, it's just the span of the columns. So can I just write it out like this? Technically speaking, I could. It's a little redundant, though. Because are those two vectors linearly independent? They're not. In fact, the span of those two vectors is the same thing as writing the span of this one vector. Right? Because 2, 4 is just a multiple of 1, 2. So what I'm trying to do when I find the column space is find a basis for the column space. So the column space is the span of the columns, but a basis for the column space are just the linearly independent columns. Well, how do we find out the linear independent columns? Well, we just look for the row reduced form. And we find those pivot columns. Right, so a basis for the column space is just the pivot columns in the matrix. So here in the row reduced form, I said this first one was a pivot column. If I just grabbed that first vector. Now in this case, it really doesn't matter. Right? If I would have grabbed the second column, it would have been fine too. But in a larger matrix, to find a basis, only certain columns will work. So you put in the row reduced echelon form and you pick out the pivot columns. So once again, what do? Grab the matrix, put it in row reduced echelon form. Questions about that one? All right, of course, we had that problem essentially on number 3. So there was a matrix A. Now the first question was a little bit different for question 3. It said, is this vector in the null space? Now you could certainly skip that one if you want. You could go on to 2 and find a basis for the null space. And then say, is this vector in the, if I look at the basis, can I construct this vector? You certainly could do this. But that's not really the purpose of that first question. That first question is there to say, what's the definition of null space? It's any vector that maps to 0. So if I took my matrix A and times it by that vector, do I get 0? If I do, then it's in the null space. Right, so that's one way you can answer this question. Just do the multiplication. If you get 0, 0, you're good. It's in the null space. Then B was finding the basis for the null space, basis for the column space. The last one was the dimension of the column space. Well, if we look at the dimension of this column space in our example problem, what is the dimension of the column space here? The dimension of the column space of A. Is it? Just 1, absolutely. The dimensions of a space are just the number of basis vectors for that space. Just the number of basis vectors. And once again, here we can really see what is the column space? It's a subspace of R2. It's any multiple of this thing. Is 3, 4 in the column space? It's not. So clearly the column space isn't all of R2, because I can pick out a whole bunch of vectors that are not in the column space. Okay. But there's a whole bunch of them from R2. So it's a subspace of R2. Is it a subspace? Is the zero vector in there? Sure, right? 0 times 1, 2. That will give me the 0 vector. So certainly a multiple of 1, 2. So 0 is in there. If I add any two vectors in here, well, I'm just going to get a multiple of 1, 2 again. If I multiply it, well, that's almost the definition of the column space here. So it really is a subspace. Okay, so that's going to finish up our talk about subspaces. From there, we jumped around a little bit. We talked about determinants after that. So as we recap the big ideas of determinants, the important property of it, the way it was defined, was such a weirdly defined thing, was it was defined to be just that number that would tell us whether there existed a unique solution for every b. Right, essentially, you take some ugly arbitrary matrix, you do the row reduction until you get to row echelon form, and you look at that last line, right? You take some matrix, you get a bunch of numbers on the diagonals, you're augmenting it with a 0, 0, 0 here, actually any number. And the only criteria was that this thing couldn't be 0. So all we do is gather up, after we do the row echelon form, whatever that ugly thing turns out to be, we call that determinant essentially. We say, is this thing equal to 0 or is it not? And so that was where the determinant was born, if you will. It was there to tell us if there existed a unique solution to ax equals b. How do we actually calculate it? We did a bunch of problems like that, so we're not going to spend too much time here. It's a mechanical process. But basically, we expanded down either a row or a column. This is like the brute force method of finding the determinant. It was smart of us to pick a good row or column. But there was also properties that allowed us to calculate the determinant. And the key properties were really the determinant of AB is equal to the determinant of A times determinant of B. And then understanding how the row operations affect the determinant. Now someone had an excellent question about this one, because this one was on the quiz as well. Number 5 on the quiz. And really, I will take other answers. In the quiz it says the determinant of A equals 3, determinant of B equals 2. What's the determinant of AB? What's the answer here? 6, right? It's the product. Sort of, right? I could easily paint a picture where that's not true. For instance, what if A was a 3 by 3 system? It certainly could have a determinant of 3. And what if B was a 2 by 2 matrix? It would certainly have a determinant of 2. But there wouldn't be a determinant of AB because I couldn't take A times B. So really I should have qualified this question on the quiz with saying both A and B are n by n. Right? They have the right dimensions to do this. I try to remove some of those qualifications when I write this up because sometimes I think they're more confusing than instructive. But I would certainly take as an answer here, there may be no solution. And if you can justify that, it's a perfectly reasonable thing to do here. Any questions about that? It kind of brings up an interesting topic here. The determinant is taking a matrix, something that lives in what we call an R n by n space, and it's mapping it to R. Now, while that can certainly be onto, can that be a one-to-one mapping? I mean, really, I can find a whole bunch of things that map to 6. Okay, you can start with a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5. It could all map to 6. And so that's kind of the question that gets brought up here. Okay, so once again, we're not going to spend a whole lot of time on determinants because it's a pretty mechanical process. That's something you can really practice and work on your own time here. All right, then we spent a kind of a short amount of time on coordinates, this idea of coordinates. Coordinates are really it's the weights. It's the weight of the basis vectors that bring us to a certain vector. It's the directions in terms of the basis vectors. So more formally, we write it out like this. These are your basis vectors, B1 through n, for your space. And you have some vector in your space. Well, by the definition of basis vectors, you can get to here as a linear combination of your basis vectors. There must be some linear combination of your basis vectors that gets you to x, because the basis vectors span the space. That means that we can take a linear combination to get to x. So that means there's some number C1, some number C2. We can add those all up to get to x. Well, those numbers are the coordinates. They are the directions. How much of this vector do we need? How much of this vector do we need to get to x? And so we write that as our little square brackets here, the coordinates of x, the directions to x, in terms of this basis, are just those numbers. Once again, it's like lazy writing. I don't want to write all this stuff over again. So I'm just going to gather up the important pieces, the coefficients. If I know the basis, all I need are these weights to get there. All right, so a quick question kind of based on that. What about this visual system here? I've given you B1 and B2. What are the coordinates to x in terms of B1 and B2? So that's the question for the paper. Once again, once you understand what coordinates are, what they mean, almost their definition, there's really no new calculations to do. If you look at that definition, all it's giving us is a vector equation, which once again is the same as a matrix equation, same as an augmented system, it's the same as everything else we've done. So what are the coordinates for this one? 1, 1. All right, this is a visual problem in this case. If I take one of these vectors and add one of these vectors, adding a tip to tail, I'm going to get to here. Okay. So I'll take one of these and one of those, it will get me to x. So the coordinates are 1, 1. Now, of course, we could do a formal calculation of that. We could say that our coordinates for x, well, by our standard coordinate system, this would be the vector 3, 0. And I'm really saying, how do I get to 3, 0 using my new basis? Well, that just means I got to find the right numbers times my first basis, which is 2, negative 1, plus some weighting of my second basis vector, which is 1, 1. And once again, we can kind of see here that 1, 1 will work. But all this is a vector equation, which is the same thing as a matrix equation. If we look at what these pieces are, well, this was just my vector in my standard basis. This is just a matrix that has the basis vectors for columns. And whatever that C1 and C2 are, that's going to be my coordinates in my new basis. That's the equation I can get from this. And this is really what we're asking on the quiz on question 2B and C. Now, if I think about it this way, though, question B says let S be the standard basis. It says if X in the standard basis has these coordinates. So we're giving you this one. It's saying here is 1, 0, 2. That's on standard basis. You should be able to figure out what B is. That's just all three of those columns here. Figure out what this piece is. So, matrix equation. We'll form the augmented thing and go ahead and solve it. The next part says if X in the new basis is this thing, it's giving us this piece. So part C is just saying if we have our B and we tell you that the coordinates in the new basis are this, what are the coordinates in the standard basis? Well, that's just matrix multiplication. Okay, so once you understand that equation and can work with that, that helps quite a bit. And of course, you can write the equation like this, Or you can write the equation like this. Because the coordinate mapping is a 1-to-1 and onto mapping. All right, any question about coordinates? Once again, once we get past the definition, it turns out to be a vector equation. All right, and the last topic, which we're currently got to, are eigenvalues, eigenvectors. This is where we're at today. To recap the first 3 sections of chapter 5, what are eigenvalues and eigenvectors? Well, lambda is an eigenvalue, and x is an eigenvector for some matrix, which is an n by n matrix, if this equation is true. If ax equals lambda x. That's the eigenvalue, eigenvector equation. And there's the process of actually finding out an x and a lambda that will work. So to find that out, we solve the determinant equation here. We solve that to find the lambdas, the eigenvalues. And then we use those eigenvalues in this equation to actually find out what x is. Remember, this equation is just doing algebra on our original equation. So we find the eigenvalues, find the eigenvectors. And then why? Well, one reason we want eigenvalues, eigenvectors, is they let us express A in this diagonalized form. Right, where P is just a matrix formed by the eigenvectors, and D is just a diagonal matrix with the eigenvalues on the diagonals. All right, so let's do this one real quick. A is 1, 2, 0, 2. And while you're working on that one, why don't you pass your quizzes, make sure your name's on them, over to here.
I don't know that we just get that here today.
All right. Work on this problem here. Pass those key. All right, don't look at the key. Finish your problem. Look at the key on your own time. All right, we're going to go through this real quick here. So, doing a little shortcut here. We can go through this definition process, but when we get to the end here, we're saying when is this thing equal to 0? And we can see it's just when lambda is equal to 1 or lambda is equal to 2. We can see that from the beginning, actually, because this is a triangular matrix. Our triangular matrices, the eigenvalues are just the diagonal elements. So then to find the eigenvectors, we use lambda equals 1. We plug it into our A minus, 1 times identity times x equals 0 equation. And when we do that, we'll get the system that looks like 0, 2, 0, 1. And we're finding the solutions to this thing. So we row reduce this thing. We get 0, 1, 0, 0 in the row reduced form. This leads me to the equations that look like x2 equals 0. And what about x1? What is x1 equal to? x1, that's our free variable in this case. So then my solutions in this case look like x1 and 0, or x1 times 1, 0. Right, so an eigenvector in this case is any multiple of 1, 0. 1, 0 is a basis for this eigenspace. And I plug in the next one, lambda equals 2. This gives me the system negative 1, 2, 0, 0. I can row reduce that if I want. It's going to be 1, negative 2. Gives me the equations x1 minus 2x2 equals 0 and x2 equals x2. So my solutions in this case turn out to be 2x2 and x2, or any multiple of 2, 1. So now I have two eigenpairs. When lambda equals 1, the eigenvector is 1, 0. When lambda equals 2, the eigenvector is 2, 1. And I can put them into that diagonal form. So the next thing we're going to do is just do that calculation. So you've seen that a couple times now, and that's on the quiz, so you can see the solution that I've written up for that one. And then the parting thought, we said, can we always find that p to make this thing diagonalizable? And we said we could do that as long as we had enough eigenvectors. We talked about the cases where we couldn't find enough eigenvectors, where we went to find the eigenvalues and we got something that looked like this. Ooh, that's lambda equals 2 repeated 4 times. Am I going to get 4 eigenvectors from this? Maybe. I might. Sometimes I could get 4, but sometimes I won't. So the question is, will we get enough eigenvectors or not? But there's another case. If we did this problem, we found all the eigenvectors. We don't have time to do the calculations, but I'll tell you what they are. Lambda equals 1 plus 2i and 1 minus 2i. Because when we solve this thing, we're going to get a quadratic. And if we think about what the solutions for quadratics are, we're finding roots of quadratic, roots of parabolas. If I had this parabola and I wanted to find the roots, well, they're this number and this number. All right, so they're equal to 0. If I want to find the roots from this parabola, it's repeated. I only have one number, it just kisses that line. So this is where I would have a lambda equals 0, lambda equals 0. But what about the roots for this parabola? I don't see what they are. But I have a theorem that says there are always roots. The problem is in this case they're complex. So we will get complex eigenvalues. The question is, what do we do with them? Do we get complex eigenvectors? If we do, can we still use those to diagonalize the matrix? And those are the questions we're going to talk about next time. So next time we're going to hit 5.5. After that, 6.1, and then we have the exam on Thursday. So we'll try to catch a little review about that on Wednesday, but this is kind of a big part of that review. All right, so go ahead and keep those sheets so you can study from the problems for today. And I will grade through these quizzes. Office hours right now. And that's it.